These transducers create an analog voltage signal, and we typically use a computer, a digital computer, to control our systems. So in order for the digital computer to react to the measurement from the transducer, we need to convert that signal into a number, a digital number, a discrete value that the binary computer, digital computer, can use. That was a lot to say, just we're motivated to perform analog to digital conversions. So here is a little picture showing our input values, and this is a continuous value. So this can have an infinite number of values between the range -5 and 5. It could be 4.1 volts, it could be 4.11, 4.1111, 4.1112. Anyway, there are an infinite number of values we can take on because it's an analog signal. And in this example, we're going to convert that using a 3-bit analog to digital converter. There are 8 possible values for a 3-bit converter, 2 to the 3rd. And here they are. So we go all the way from 000 to 111, and all the permutations or combinations in there. So 0 to 7 are our 8 values. Now we're going to have to divide this range of voltages into 8 values. So there's going to be a certain bin size, and it turns out to be 1 1/4 volts. So that means that all the voltages from 5 down to 3 3/4 will get lumped into this 111 bin. So they'll all be treated as an integer 7. And here is a figure showing what that looks like. Not this figure, this figure. Here in purple is our continuous voltage, our continuous signal, and if we wanted to break it up into a discrete value, again with a 3-bit converter, then you can see the 8 different bins that we have. So all the voltages here, in this figure the range is 0 to 10 instead of -5 to 5, but anyway, here we have all the voltages between 8 3/4 and 10 are just going to be treated as, they're all going to be treated the same. So we have 8 possible values, and our range was 10 volts. So that gives us that the step size is 1 1/4 volts, or the resolution is another term for that. Here are the size of the bins. It is the resolution. Okay, here's the size of the bin. It's the resolution. And then we're going to have to choose some value to treat input voltages that fall within this bin as. So we're just going to treat those as the center value. What I mean is, for example, if we have an input of 3.6 volts, then that'll convert to a integer or decimal 6. So it's in this bin, and we'll just consider that 3.6 as 3.125. Likewise, if we had 2.9 volts input voltage, then it would fall in this range, and we'll just treat that 2.9 as 3.125. So there's going to be some error between our input and the value that we assign to it after the digital conversion. And that error is just, the biggest error we could have is half of the resolution. So if we were at the maximum value for this range, then the error between that and the result of our conversion would be half of the range. And that gives us an expression for the quantization uncertainty. It's just half of the resolution. So here's an equation for that, half of the range divided by 2 to the m, where m is the number of bits. One important piece of hardware is the dual slope integrator. This is just one of the many ways that we can perform an analog to digital conversion. The way this works roughly is we connect our input voltage to an integrator circuit and measure the amount of time. Then we connect the integrator circuit to a known negative reference voltage. So the slope goes down from that point. And we measure how long it takes for the voltage to reach 0. So that's what the comparator is for. Whenever it reaches 0, then the comparator will provide a signal. So the vertical distance here is just the product of the slope and the time. So we know the time, we know this voltage, which is the slope. So knowing those things, we can get the input voltage is the reference voltage times the ratio of the downslope time to the upslope time. Sampling is the sampling rate is an important consideration. So sampling whenever we have a time-varying signal, we're not just going to take one measurement of it. We'll take measurements periodically. And that's another way that we are discretizing our continuous signal. So the continuous signal, not only can it take on an infinite number of different values, but it also changes continuously with time. So back to this figure, here's our continuous signal. So you can have all these values, but it's also changing with time. And whenever we perform an analog to digital conversion, that conversion process takes a finite amount of time, no matter what method we use. And so we don't know the value of the input signal between sampling times. So for example, so we have to assume something about it. This is called a zero order hold. And in this case, we just assume that the input voltage is constant between one sample and the next. So that would look like this. So this shows how we are discretizing the numerical value of our input signal, and we're also discretizing it with respect to time. So we only know it at certain intervals. Now the frequency at which we sample our signal is important. So here is an example input signal. So say it's a sinusoid, and this is an important input signal to consider because, as we saw with the Fourier transform, any input signal can be decomposed into a summation of sinusoids. So let's look at this sinusoidal input. If we sample that at a frequency f samp, which has a sampling period of delta t, and our current time is just n times delta t, so that's the meaning of this letter n, then our observed sampled signal at n delta t is just going to be sine of 2 pi frequency times n delta t. So we replace time with n times delta t. So this n is an integer, so n delta t is going to have discrete values. Now, there are frequencies. Whenever we sample at a given rate, there are input frequencies that can appear the same as other input frequencies, and this is called aliasing. So after we sample the data, we would have no way of knowing what the input frequency was if there's aliasing going on. We'll look at this a little bit more. So for example, if we had these frequencies, then the observed sampled signal would look like this, and we end up with 2 pi f times n delta t minus 2 pi m times n. Since m and n are integers, this is identical to sine of 2 pi f n delta t. So there are some frequencies that would look the exact same as another frequency f. Different input signals appear to be the same. And this gives us an expression for what that observed or apparent frequency is going to be in terms of our sampling frequency and the true input frequency. A few illustrations should help clarify this. Again, we have our expressions. So say, for example, we have a 10 hertz input signal and we sample it at 10 hertz. Well, using this equation, we're going to have an apparent signal of 0 hertz. So it's going to look like a DC signal. And here is what I'm talking about. So here's our 10 hertz input signal. See if I can make this a little bigger. And we sample it at 10 times a second. So every time we sample it, it's at the same value. So this looks like just a DC signal. So this is our apparent signal. If we reconstructed it, that would be our apparent signal. Another example, say we were sampling at 10 hertz. I'm sorry, we have a 10 hertz input signal. We're sampling at 11 hertz. This expression says that we would end up with an apparent 1 hertz signal. So these sampled values are going to be indistinguishable from the sampled values if we had a 1 hertz input signal. Again, we'll illustrate that. Here's our input signal. Sample it at 11 hertz now, and this looks the same as a 1 hertz input signal. So here's an example where two frequencies can appear to be the same whenever we sample them. We have 10 hertz input, but it looks the same as if we had 1 hertz input. Another example, okay, well this one isn't written quite right, so let's not look at that line. Say we had 12 hertz input signal. We sampled it at 22 hertz. It would look like a 10 hertz signal. It would look, yeah, if we reconstructed that, it would look like a 10 hertz signal. So in other words, it would have the same sample data as a 10 hertz input signal. So you see that the apparent value is given by this equation. So it's the difference between the sampled frequency and the input frequency, unless a certain condition is met, and then we'll get to that in a second. So here's another one, sampling 10 hertz at 15 hertz, it looks like 5 hertz. Sampling 10 hertz at 19 hertz looks like 9 hertz. And then what if we sample 10 hertz at 20 hertz? Then we'd be back to the same position we were before. Oh, 5 hertz, yeah, there you go. It will look like a DC signal. So integer multiples of the input, if we sample at integer multiples of the input signal, then we're going to end up with a DC signal, so zero change. If we go ahead and sample just one little bit above the twice the input signal frequency, excuse me. So our input is 10 hertz. We sample at 20.1 hertz. Then we're able to reconstruct that 10 hertz input signal. And when I say reconstruct, I mean use the Shannon formula, where if we have our sample data, we are able to reconstruct the input signal. The way that you can ensure that there's no aliasing, so the way that you can ensure that there are no frequencies that look the same as other frequencies, is if you sample more than 2 times the maximum input frequency. So for this example, or for these pictures, whenever we sampled at more than 2 times our input frequency, we were able to reconstruct the input frequency. So, and then if we had anything below 10 for this sampling frequency, we would be able to reconstruct it. Now, if there are frequencies, okay, so you can do that. You can determine your sampling frequency using this criterion if you know the maximum frequency of your input. If you don't know the maximum frequency of your input, you can apply a low-pass filter to ensure that you don't have any higher frequencies, and then sample your signal after the filter. So for this example, we would want a 10 hertz low-pass filter. A digital to analog converter is important for a couple of reasons. One is if we want to be able to generate a control signal to control some actuator or control some process, then our computer is going to come up with a digital number and we need to convert that to an analog voltage. So we would use a digital to analog converter for that. Another way is for some different analog to digital conversions, they need to come up with different values for comparing the input voltage too. And to do that, you'd use a digital to analog converter. So that way the computer can come up with these known voltages, reference voltages, to compare the input against. Now here's a digital to analog converter using, well, an op amp, but let's start with just this op amp configuration. The output voltage is given by the gain, the sum of the gains and the input voltages. So the gain for E3 is RF over R3, and the gain for E2 is RF over R2, and the gain for E1. So anyway, we end up with the output voltage is the sum of these input voltages times their gains. The way that's used for a digital to analog converter is we would have discrete switches for all of these different resistors, and then the output voltage would be based on the combination of these discrete values. So if we had switch 0 closed, then the output voltage is going to be RF over 128 times the reference voltage. And if we had switch 7 closed, the output voltage would be RF over 1 times EREF. So this switch is going to provide a voltage 128 times bigger than this switch. So it's known as the most significant bit, and 0 is the least significant bit because it affects the output the least. The feedback resistor value is 2 to the n, so that exponential minus 1 times the resistor value that we use for each of these lines. So for example, for this 8-bit digital to analog converter, the feedback resistance value would be 255 times R. And with that value, then our output voltage would be somewhere in the range from 0 to EREF.